In this project, my objective was to develop a reliable regressor to predict residential energy consumption using the RECS dataset, with performance evaluated using mean absolute error, because the competition metric is MAE rather than MSE. My modeling decision focused on robustness to outliers and the interpretability of prediction error in absolute units. I began by carefully examining the structure of the dataset. The target variable is labeled target, and the test set includes an ID column that must be perceived exactly in the final submission. One of the most important observations during exploratory analysis was the presence of coded integer values such as -2 appearing frequently in variables like stories, solar, e- equipment, and the fuel heat. Rather than treating these as missing value, I analyzed their frequency and distribution and determined that they represent meaningful categorical states, such as not applicable. Therefore, I perceived this value instead of converting them to NaN. Since removing them degrade cross-validate MAE performance, feature preprocessing was implemented using a column transformer pipeline to avoid data leakage. Categorical variables were identified as object type columns as well as integer coded variables with low cardinality, since many RECS variables represent discrete survey categories rather than continuous measurements. These categorical features were cased to string and warm-hot encoded with dense output to ensure com compatibility with the gradient boosting estimator. Numerical features were imputed using median imputation to perceive distribution robustness. For the regression model, I select his gradient boosting regressor with the loss function set to absolute error, which direct optimized for MAE. This choice aligns the training objective with the evaluation metric, reducing metric mismatch and improving leaderboard consistency compared to linear models such as Ridge. Tree-based boosting better captures nonlinear interactions between variables such as square footage, heating equipment type, region, and solar presence. I turned the model manually rather than using a full hyper hyperparameter search in order to perceive notebook clarity and reproducibility. The final configuration used a reduced learning rate, increased the number of boosting interaction, moderate tree dips, and mild L2 regulation. Lower learning rates combined with more boosting stage improved the stability and reduced variance, while regularization helps control overfitting under MAE loss. Model performance was evaluated using five-fold cross-validation with shuffling. Cross-validation MAE was stable across folds, with low standard deviation, indicating consistent generalization performance. The learning curve and analysis showed that as training size increased, validation MAE decreased and stabilized while training MAE gradually increased toward validation MAE. This pattern indicates that the model is not severely overfitting and that additional data contributes positively to generalization. An important modeling insight was that cheating coded categorical variables correctly had a large impact on MAE, MAE than simple turning hyperparameters. When negative 2 values were replaced with NaN and imputed, MAE worsened because structural information was lost. Preserving these as categorical states allowed the boosting model to learn segment-specific effects, particularly in housing configuration and equipment variables. After confirming cross-validated performance, I retrained the final model on the 4 training datasets and generate the prediction for the test set. The submission file was constrained by copying the ID column exactly from the test data and pairing it with the predict values under the requirement target column name. This ensures Kaggle validation capability overall. My modeling strategy balanced robustness, interpretability, and metric alignment. By carefully handling categorical encodings, preserving meaningful coded values, and selecting a boosting model optimized for MAE, I was able to achieve stable cross-validated performance and competitive prediction ac- uh, accuracy for residential energy consumption. If I were to extend this further, I would explore model ensembling between gradient boosting and random forest to potentially reduce MAE marginally, as well as investigates feature interactions such as ratio between square footage and number of rooms. However, the current model already demonstrates strong bias variance balance and consistent generalization behavior under the MAE metric.